Good morning to all. Today we're going to see the topic antenna gain and antenna's efficiency. Okay, gain of the antenna. It is an ability of an antenna to radiate maximum power in a given direction. It can either radiate or absorb. So generally, it is an ability of the antenna to radiate maximum power in a given direction or to absorb power efficiently. The definition of it is defined as the ratio of maximum radiation intensity from a subject antenna to maximum radiation intensity from a reference antenna. Very simple. Subject antenna. This is maximum radiation intensity. A maximum radiation intensity from a subject antenna. Subject antenna is nothing but the antenna for which we are going to find the gain. So maximum radiation intensity from a subject antenna to maximum radiation intensity from a reference antenna. This reference antenna is generally an isotropic antenna. That is, this isotropic antenna is a standard antenna that radiates power in all directions. So the gain of an antenna can be found out using this formula. Maximum radiation intensity from a subject antenna to maximum radiation intensity from a reference antenna. Okay, this can also be represented as we know before gain of the alpha is written as G. So gain is equal to U is radiation intensity, maximum radiation intensity from a subject antenna. This is theta phi. Theta phi is space coordinate because this is radiation. We want to radiate this power in free space from transmitter to receiver. It is going to go in free space. So this theta phi is the coordinates of free space. So U is radiation intensity, maximum radiated power of the subject antenna to maximum radiation intensity of the reference antenna. So this is represented in this equation. Generally, gain is measured in dB. Gain in terms of power. If you put gain in terms of power, this is in terms of radiation intensity. If you put gain in terms of power, maximum power received from a subject antenna to maximum power received by a reference antenna. So this is a formula to find gain in terms of power. Okay. The next, there are two types of gain in antenna. One is directive gain, which is represented as G suffix P. Other one is power gain, which is represented as G suffix P. You'll see what is this in detail. Directive gain. All the practical antennas concentrate their radiation power in a particular direction. Generally, impractical, all antennas concentrate the radiation power in a particular direction because from source to destination, if they have to go, they will concentrate the power in a particular direction. The extent to which a particular antenna concentrates its energy is called directive gain. So the extent to which a particular antenna concentrates its energy is called as directive gain. So directive gain, as we know, it is VD is equal to radiation intensity in a particular direction divided by average radiated power. So as I told you, GD is directive gain. It is in free space, so theta comma phi, and radiation intensity in a particular direction. 4 pi area is 4 pi U radiation of free space divided by average power radiated. Power radiated is WR. Radiated power. R is radiated, W is power. So this is an equation to find directive gain. Next one, power gain. Directive gain is nothing but how much an antenna concentrates in a particular direction. It's called directive gain. Then power gain. It compares the radiated power density of an actual antenna with an isotropic antenna. That is, it compares radiated power density of an actual antenna with an isotropic antenna. Isotropic antenna is nothing but a reference antenna. So it compares how much an antenna is actually radiated power density with actual radiated density compared with isotropic antenna. So radiated intensity in a given direction divided by average total input power. So as we know, this is in free space, so radiation is U in free space divided by, since it is in 4 pi is a formula, it is in space, it is 4 pi area, WT, if you go on the numerators and you get this equation, WT is nothing but transmitted power. That the WR is radiated power. Here, WT is transmitted power. The difference between GT and GA, that is directive gain and power gain, is both the equations are almost same. 4 pi u in free space divided by WR. Here 4 pi u in free space divided by WT. So WT and WR there, that is radiated power radiated here, power transmitted. Radiated is different, transmitted. Transmitted is total power transmitted. Radiation is different. So the WT is equal to power radiated plus power loss. Example, if you're transmitting a data from one source to destination, you will send certain amount of data. But when you transmit, there is a radiation, it will get radiated. If you transmit, it will radiate, but there are few losses because it is going in space. Data will be lost, so power will be lost here. So total power transmitted is equal to power radiated plus power loss. When an antenna is transmitting power transmitting power, a few amount of power is lost. Then lost power is WL, and the remaining power is transmitted. So WR. The relation between power gain and directive power. We know power gain GP, directive power W. So this is eta. So eta is efficiency factor, which is generally between 0 to 1. If the efficiency factor is 1, then GP will be equal to GD. Okay, the next one. Antenna radiation efficiency. It is defined as the ratio of power radiated by an antenna to the total input power. How much power is radiated to total amount of power being inputted. As I told you, the input will be high, but while radiation, there will be loss. So there will be a difference. So it is the ratio between power radiated by an antenna to the total power input supplied to the antenna. It is generally denoted by the letter K or efficiency 0 to 1. We know efficiency is here, eta. So power radiated divided by total input power. Power rated PR, total input power P in. We know that, as I told you before, input power will have radiated power plus power loss, because I told you input will be there. Example, we are giving input to a system, but it will transfer the data. But while transferring, there will be losses. So input power will be equal to power radiated plus power loss. This power loss is ohmic loss. So K is equal to PR by PN. By what is K? Power efficiency is K. So power efficiency K is equal to P, power radiated by power input. Power input can be replaced by radiated power plus power loss. So this is replaced by power radiated plus power loss. Okay, this is radiated. So in term, if the current is flowing through the antenna is I. So considering the power current flowing through the antenna is I, then P is equal to IR. I square R, we know the formula P is equal to I square R. P NAND is equal to, that is instead of P NAND is equal to I square by IR. Because this is radiated power. Radiated power is only PR. Then input power. For input power, it is equal to power radiated plus power loss. So instead of PM, you will be writing as I square R PR, power radiated plus I square R plus into power loss. So substitute these two in this equation, what we'll get? We'll get K efficiency K is equal to I square R into both the I square into R plus RL. I square R, I square R, I square get cancelled. So the remaining is R divided by RR plus RL. In terms of efficiency, that is in efficiency, in nothing in terms of percentage you get into 100. For an ideal antenna, we have 100% efficiency, but it is not possible because there will be losses. It transmits all power, it feeds. This is not possible. An ideal antenna is nothing but it transmits all the power that it gets, but it is not possible. Thank you.